Okay. So welcome everyone. So it's my pleasure to welcome Krishna Pillutla, who is an assistant professor and the Narayanan Family Foundation Fellow at Wadhwani School of Data Science and AI at IIT Madras. So previously he has been a visiting researcher at Google Research in the Federated Learning team. So he obtained his PhD at the University of Washington, MS from Carnegie Mellon, and BTech from IIT Bombay. Krishna's research has been recognized by Newry's Outstanding Paper Award, a JP Morgan PhD Fellowship, and two American Statistical Association Student Paper Award honorable mentions. So today he's going to talk about near optimal private learning with correlated noise mechanisms. So welcome.
Thank you so much for the kind invitation. I'm so happy to be here. So today's topic is about about correlated noise mechanisms, but we'll start with thanking the collaborators. These are folks I worked with at Google during my time there and continue to collaborate with some of them. So this XKCD comic is one of my favorites. Many of you would have seen it. It's also remarkably prescient because back in 2019, it predicted that language models would leak information about the data they were trained on. And a couple of years later, researchers found that this was indeed the case. Language models do leak information about their data, and they do so quite reliably with a very high extraction rate. And why target language models alone? Other generative models too. Here's an example of a paper that shows images being generated being very similar to the ones they were trained on. So this kind of leakage, the way to the standard way to prevent this is differential privacy. So if we think of our learning process as a randomized algorithm which takes in a bunch of data and returns a sample from some probability distribution, in this case over models which are being trained. What differential privacy says is if I change my data set by a little bit, say for example adding or removing some data, the output distribution of the algorithm doesn't change by very much in a very precisely quantifiable sense. So it turns out that this does actually address our problem of memorization to a fair extent. This left side plot shows that as we change this privacy parameter, which is the gap between the distributions, this loss that we get actually gets very close to the non-private loss, but the memorization behavior on the right is qualitatively different, even at these very low, almost vacuous privacy, low privacy parameters. So the name of the game here is generally to attain better privacy utility trade-offs along with reasonable computation cost. Right? So we want this curve to go lower. At each privacy level, we want better loss. Or if we are looking at accuracies, we want higher accuracies, right, at each point. So we want Pareto dominance over what is currently being done.
In this graph, do you really mean 10 to the 9?
It is 10 to the 9, yes.
What is 10 to the 9?
So this epsilon is a measure of the gap between those distributions. Okay. So that parameter is 10 to the 9, which is like vacuous.
So 10 to 9 means more privacy or
less privacy?
Less privacy.
Yeah.
So the ratio of the probabilities is around 3 to 10 to the 9.
Yeah, we are allowed to go this basically makes no sense from a theoretical perspective to have such large values, but there is a qualitative difference from even that very small amount of noise.
But even 10 makes sense. I mean, even 10 is what? Like about the probability is around.
Sorry, it's e to the 10 to the 9.
Yeah.
What? Yeah, so log likelihood ratio is 10 to the 9. Yeah, is allowed to go as large as 10 to the 9. Yeah, so usually in practice,
also but in these situations, the probability is also very small, right? So
no, but yeah, right. It's in practice we usually are around the 10 range, right? Between 10 to 100 is what in machine learning setting. Closer to 10 is what we typically look at.
These are high dimensional distributions or what kind of?
Yeah, so these are thinking about distributions in model parameter space.
Mm-hmm. But what's the dimension? Will that be relevant to the numbers, no?
So yeah, for this, so actually for this setting, I think it's like a small model, so maybe a few million, but that doesn't change because we look at the standard deviation per coordinate. Oh, yeah. So, I mean, this is just motivation so far. So our setting is we're interested in training models with differential privacy. So the standard setting is we want to find our model parameters, which we are representing as a vector in n dimensions. And we want to minimize the expected loss of making a prediction on some point x drawn from a distribution p under the model theta. So the standard approach to solving this, and especially in a deep learning setting, is a variant of stochastic gradient descent. So there are two changes made to standard stochastic gradient descent, right? So one of them is that we clip our gradients, right? So the gradient coming from each example is clipped to a certain norm, say 1, in L2 norm. And then we add noise, right, to these clipped gradients. And this noise typically is IIT Gaussian noise, both coordinate-wise and per iteration, right? So in each iteration, we sample fresh noise and add that. So what this looks like in practice is we typically privatize individual mini batch gradients, right? So in the first line, it's the first iteration. We sample some data, compute our clip gradients, add some noise, and then this is a private gradient estimator in iteration 0, and then the same thing in iteration 1, and so on. So one thing that happens here is this noise just accumulates across iterations. And that can potentially hurt learning performance. So a class of approaches that recently gained prominence in about 4 years now is to use noise which is anti-correlated across iterations, right? So essentially what happens is in the first iteration we get our gradient G0, we add some fresh noise. In our first iteration, we sample fresh noise Z1 and then subtract out a component of the noise Z0 that we previously sampled, right? And same way in the next iteration, we sample fresh noise and subtract out parts of the old noise, right? So the basic reason why we would hope this helps learning is because this prevents this noise from accumulating. But we have to make sure that we can still guarantee privacy, which I'll come to later. And it's been found empirically that this approach Pareto dominates using independent noise, right? So this is from this paper in 2023 on training a language model, small language model on Stack Overflow data set. So it's empirically it does quite well, and in fact, even in industry, this has been used by Google to train the next word prediction models on our phone keyboards, right? So this algorithm has also been quite impactful in practice.
Not with what
Yeah, good point. They're probably around the ballpark of 8. Actually, in one setting, they got like a really small one, order one, but usually around 8 is what we expect. So, of course, finding the right noise coefficients is the make or break component of this, right? And one approach, the most commonly used approach, is to come up with a surrogate based on the trajectories in parameter space, right? So suppose this black line is the non-noisy trajectory. How close uniformly is the noisy trajectory, right? So what's the maximum deviation at any point? Is one such surrogate metric which we will consider today. It's called the max loss, right? So the first part of the talk, I'm going to focus on the time complexity of noise generation, right? So suppose so in each iteration I need to subtract out parts of noise that I've previously sampled. If I do it naively, it's going to take quadratic time complexity. So can we do it better? So our approach is to approximate these noise coefficients, which I've denoted here as the C tau prime notation, which will become clear later about why the prime is there. So it turns out that we approximate those with a class of coefficients which can be computed recursively. So that gives us improved time complexity. So we get polylog n with approximately the best possible error, right? So that's going to be the first part. And the key here is relies on constructing a rational approximation to the square root function, which is a very interesting connection in my opinion. And this approach has also led to an improvement over Google's previous production language model across various languages. This plot shows the Portuguese language model, where we again see that Pareto dominance. So this is a production system. So getting good computational cost is not negotiable, right? So previous approach, which had good computational cost, turned out to be not as good empirically, right? So this improves that. So in the second part, which I will only touch upon very briefly, if at all, depending on the time, we are going to take a closer look at this surrogate objective. We are not optimizing for the learning performance. This is purely about trajectories in parameter space. So some previous work showed that you can construct these noise coefficients where you have the same surrogate objective, but their learning performance is different, right? So this orange one converges and red one diverges, right? So what's the relationship? Can we say something provable in learning problems, right? And so in the second part, we show that for linear regression problems in particular, we get a strict separation between using independent noise and correlated noise. And it's in terms of some sort of underlying effective dimension of the problem.
But this is noise for what? So with the even if you don't want price, so what's
I'll come to the details. Yeah. So basically, using correlated noise versus independent noise.
but if you don't use any noise, that's the ground.
Yeah. So we are going to scale the noise as if we wanted privacy, right? Because I'll come to it. Okay. So I'm going to start with some background here, and let's go over some of these details. And much of this is based on a recent monograph that we put out on this topic. Okay, so as I said, differential privacy is about measuring how much changes to the dataset leads to changes in the output distribution. So let's make that precise using this notion of zero concentrated differential privacy. Instead of epsilon, we are going to use rho. That's the convention for concentrated DP. The basic idea is that the gap between distributions is formalized as a Renyi divergence. Right? So you want the Renyi divergence between the distribution before and after changing the dataset to be close. So the alpha Renyi divergence will be at most rho times alpha, and we want this for all alpha, basically. So
in this, so one would be K divergence, and infinity would be just taking the
log likelihood ratio, yeah. That's right.
And why not use, let's say, 0 to 1 also you have?
It becomes tricky. Yeah. So basically, the underlying reason we want to do this is, okay, so without going into too many details, we can work it out on the board later, but we want to control the tails of a certain random variable, right? So we are talking about distinguishing between two distributions. So it's like, what does the log likelihood ratio look like? And we want to control the tails of the log likelihood ratio. And this condition is the same as that being sub-Gaussian, essentially. Okay, so let's derive this correlated noise mechanism. So let's start with our stochastic gradient descent update without any additional noise in this, and let's roll it out, right? So recursively roll it out all the way to theta 0. So the first thing that we're going to try and do here is to compute the running sum of these gradients, right? The prefix sum. So at any iteration t, we want the sum up to iteration t. So it's convenient to write those in a matrix. So let's stack all of those gradients in a matrix G as rows. And our prefix sums can then be obtained as a linear operation on that matrix G, which we are going to denote by another matrix A. It's just the lower triangular matrix of all ones, right? So I'm going to refer to that as the prefix sum matrix. So if we take our independent noise algorithm, in this matrix notation, what's happening is we are sampling each row of this matrix is a different time point, right? So we are sampling IIT rows basically. And then after that, we compute the stochastic gradient descent update, which in our matrix notation is represented by left multiplication with the prefix sum matrix. Right? Because SGD implicitly like computes the prefix sum of all the gradients so far. Okay, so for correlated noise mechanisms, our starting point is to take a factorization of this A matrix into B times C, where both B and C are assumed to be lower triangular and invertible. Both assumptions can be lifted, but let's keep it simple now. So essentially, what we are going to do is add some noise inside this, right? So we multiply our gradients by C, add the noise, and then multiply the whole thing by B. Right, so this B times C is A, right? So here in expectation, this is 0, is just 0 mean Gaussian noise. So in expectation, we are getting the right thing. It's just that these correlations introduced in the noise are a little different because of where the noise is being injected, right? So to see that a little more clearly, let's take this substitute B as AC inverse back in that expression that we wrote earlier. And by rewriting this expression a little bit, what we see is that we said A is the SGD update. So the noise that's being added to the gradients would be the rows of this C inverse Z matrix, right? So Z is IIT Gaussian. So C inverse Z is now correlated by this matrix C inverse. Right? So that's where the correlation is happening, and here's a picture to depict that. So one thing in the example that I took earlier, these coefficients are basically the lower triangular part of the C inverse matrix, and I just assume that the diagonal is all ones. In a lot of cases, that does turn out to be the case. Okay, so we need to give. So what is the privacy bound? Like clearly choosing these correlations changes the privacy bound, because if I just subtract everything out, then I'm potentially losing out on privacy, right? So this matrix shows up in the privacy bound somehow. So the assumption we use throughout is that each data point only appears once, right? So all my gradients, basically, if I change my data set, what I'm assuming is that one row of my matrix is changing, right? If that assumption was not valid, multiple rows would change. We can work with that. It just becomes a little more complicated. So that's the streaming assumption, which will hold throughout. So essentially, the element-wise, so when I say variance of Z, I mean Z is a matrix, so I mean it's IID throughout, right? So it's the variance of each element of Z, right? So to get this rho concentrated DP guarantee, I need the variance to scale as 1 over rho times some property of this matrix C, right?
So very equal to BC. So that is not there is no unique decomposition like
No.
So which one do you choose?
It's our choice. So we are
You
going
choose any one C, any
Yeah.
any invertible lower triangular C that gives you a V, and then you use
Yeah. So now I have to scale my noise accordingly. But then how do I choose the C? It's to minimize the surrogate.
A is
A is fixed. It comes from our optimizer. So A is always fixed. Yeah. So the choice of C plays a role in the variance of the noise. So it's this C column norm is basically the largest L2 norm of any column of C. Right. So that scales the noise variance. So let's make a couple of observations about this variance expression. So I mentioned that if I
Z is N0I times the square root of Z. So that
element wise, yes.
Yeah.
Element wise, yeah. N01 because
N01 times the square root of Z.
Yes, exactly. So we talked about this privacy parameter as being a gap. So large gap means more information is potentially leaked about the data point, which is the difference between the two data sets, right? So if this row is large, it's the low privacy regime. If row is small, it's a high privacy regime, right? And if row is small, that means our variance is going to be larger, which kind of makes sense. We don't get privacy for free, right? We have to add more noise if we want more privacy. So that checks out. That generally shows up in every differential privacy guarantee. So the second thing is, of course, if we take this C matrix to be identity, we recover independent noise. And what we see from this expression is, again, if I normalize the diagonal of the C matrix to be all ones, the column norm of the C matrix is never smaller than one, and because there's a one here, like anything has to be larger than that. So independent noise has the smallest variance of the IID noise, right, of this Z. So essentially what's happening is the variance of the noise I add in one iteration is larger, but the noise cancels out across time, right? Across model dimensions is all independent. So for all practical purposes, we can think of it as one dimension and the same thing is replicated, but the cancellations happen across time. Okay. All right. So the next second to last thing in the background is our surrogate, right? So this is what we actually optimize to find the C matrix. So how far is our trajectory moving? So this S is the matrix of prefix sums, as I said, and S hat is would be the prefix sums that we estimate. Now we want those to be uniformly close. So we'll pick up the tth row and make sure that the worst case across all time is closed in square delta norm sense. So we can actually like simplify this expression. So as I mentioned, it's an unbiased estimator of the true prefix sums. So the difference between them is some noise term with this matrix B. So we can just simplify that, and it turns out it depends on the largest L2 norm of any row of B, right? So calling that the row norm. So again, our variance of Z comes from the column norm of C. So those are really the two things that matter here. And then we have something depending on the privacy level row, on the dimension, and so on. Things that are not related to the actual factorization that we choose, right? So for the purpose of the factorization, what we care about, and this is how we define the max loss, is the row norm of B times the column norm of C. And throughout, the constraint is that B times C is the prefix sum matrix A. Right. So by optimizing for this is how we find the correlations that we actually use in practice. Okay, so as our baseline is going to be independent noise. So if we take C to be identity, that means B equals A. This is the prefix sum matrix. So what is our max loss going to be? The column norm of identity is 1. The row norm of this is the norm of the last row, right? So it'll be square root of n. Right? So that's going to be our baseline. Anything we do will be better than that. And this, by the way, this is also like what you would get with the random walk, right? So independent noise keeps adding up, random walk. Okay. So throughout this talk, we'll restrict ourselves to Toeplitz matrices. That just means along every diagonal, we have the same value, right? So the main diagonal is all C0, the diagonal below that is all C1, and of course, they're all lower triangular throughout as well, right? So taking Toeplitz matrices is good analytically, it makes our life much simpler. But there's a stronger reason to use Toeplitz matrices. It turns out that we don't lose much by restricting ourselves to be Toeplitz. Animation before that, yeah. So let's say opt is the best possible max loss we can obtain for any factorization. And if we impose the lower triangle and Toeplitz constraint, let's call it as opt-to, right? So that's the best Toeplitz mechanism. So we are justified to restrict ourselves to this class of Toeplitz matrices, because doing so only leads to a small increase in the suboptimality. It's a fixed constant one. Like in fact,
A that A, this is called A that A equal to that column.
Yeah, lower triangular one. So everything I say is for A being fixed.
But that one particular, for this one you probably need that it's also the lower triangular. So is this true for any lower triangular A?
A is no. So this is all true for A being the lower triangular matrix of all ones.
Yeah.
So that is fixed throughout. Yeah. So in fact, I mean, if you look at it empirically, it's much smaller than 1. It's closer to like 0.35 or something. But you know, this is take it to be 1, and this is independent of the size of the problem. So the other thing which is known is that this both opt and opt scale as log n by pi, right? Plus a small additive constant, right? So we know the precise is the precise constant as well as 1 by pi. Right, so our goal will be also to maintain that leading order term. Okay, and this is much better than root n. So we're doing better than the baseline, at least in terms of our surrogate. And by the way, we can also find this optimal Topliss factorization involves taking B equals C. That's not very surprising because of the symmetries in the row norm and column norm, right? So for a Topliss matrix, the row norm and the column norm are equal, right? The last row has the largest row norm, the first column has the largest column norm, and the elements are the same, right? So this is not surprising that this is the optimal factorization. So we can also write down the square root of this. It turns out that the below diagonal entries scale as t power minus 3 by 2. That's just a tidbit. It's not going to be useful going forward. It's just interesting. Okay. So that brings us to the end of the background. So let's dive into part 1. Any questions at this point? Yeah.
Could you go to the slide where you showed where the noise adds up? It was, I think, at the very beginning.
Yeah, this one.
Yeah. So as you said, that the main problem is that the noise accumulates, right? So why don't you do something like also clip the noise as you go along in the training process, or I mean, from the simple looks of it, you can have many possible ways to deal with the addition part of the noise. So why not?
Yeah, we have to be very careful that at each point we don't sacrifice the privacy guarantees.
Ah, I see. Okay.
Yeah, so we have to be very careful with how we add the noise, right? So even when we did this correlated noise, we blew up the variance by a very precise factor so that we still get our privacy guarantees. Any other questions?
One question.
Yeah.
So there was this graph, right, where you had no noise, and then you're adding correlated noise, so you're not so far away from the true gradients.
Yeah.
There must be something that guarantees that if you're not too far off from the true gradients, then the final loss won't be too far away. There has to be some sort of this thing.
When you say final loss, you mean the surrogate or in terms of the learning objective?
Yeah.
So you need something like strong convexity for that. Yeah. I mean,
The loss function.
yeah. There are some cases where you can make that precise.
I see.
Yeah. But this is an expectation, right? And by the way, like in practice, these are used on deep learning problems where, no, strong convexity probably doesn't hold globally at all. I mean, doesn't hold at all and probably only holds locally, if at all, right? Yeah. Any other questions? Okay, so let's get into the first part. Just to recall here, the correlated noise that we care about is this C inverse Z. That's the one that's being added to the gradients. Like if you go and implement it in PyTorch or something, like the C inverse Z is the noise that you want to add to the gradients before throwing it to the optimizer. So to recall the issue, it's one of time complexity. In each iteration, we need to cancel out. This is supposed to be T minus tau. So you need to cancel out some noise from past iterations, and you have to do it over all the previous iterations. So what can we do there? let's summarize what we know so far. So we know we have the independent noise, and then we have the optimal correlated noise. We've seen their surrogate max loss values. It's like square root n and log n. And then this dimension is the best you can do, right? Like you have to take all the model parameters, right? But this is bad because it's in each step you're paying linear cost, right? So one approach, this is just summarizing what we've discussed so far, nothing new in this slide yet. So one approach which has been tried here is to take banded matrices, right? So essentially only enforce some number of non-zero elements, right? You can enforce that constraint either on the C matrix or on the C inverse matrix. From a computational perspective, nothing changes. From a max loss perspective, also is the same because of the symmetry in the problem. So, so essentially, if you have B non-zero entries, then your noise generation cost scales as B, not as the number of steps, right? So that gives us overall linear complexity, which is good. But unfortunately, the catch here is that if you take this B to be very small, your max loss suffers, right? If you take it anything to be little of n, you're going to be in trouble, right? So that is unfortunate. So what can we do? Like our approach here was to start. So this was to start with, okay, so what can we implement recursively, right? So let's say we have a nice exponentially decaying sequence, alpha times lambda power t. So everywhere, whenever you see z tau, it's zt minus tau. That's a typo which got copy pasted in each slide. Apologies for that. Okay, it's correct here. So so we want to compute this, and we can do it recursively for an exponentially decaying sequence, right? So we just include this extra lambda factor in what we computed so far, and then add that alpha to the new noise, right? So this is the update. So the old noise that we computed, we multiplied by lambda and add the new noise with an alpha factor, and we get the right correlated noise for the next step, right? So this can be computed very efficiently on the fly. Now, if we have a sum of two exponentials, the noise that we want to compute is linear in these coefficients, this CT prime, right? So essentially, we can do the same thing, like we can break it down into sum of two exponential sequences, exponentially decaying sequences, have a separate recursion for each one, right? And we get something which does not depend on the number of iterations. So what the additional cost we need to pay is we need to store these extra vectors WT1 and WT2, right, in order to continue these recursions, right? So we're paying an extra storage cost of a dimension factor here. So our approach here, which we call buffered linear toplets, is to just do the same thing, but take a sum of d exponentials, right? Some parameters, alpha is and lambda is that we have to find. But once we have those parameters, and we want to find those parameters such that we approximate these optimal coefficients. But provided we can find those, we are good because we get this overall linear complexity by recursively updating everything, and we are paying an extra d times dimension. So it's like, so if d is 4, your memory requirement is now the same as storing 4 gradients instead of 1, which is all right in a vast number of applications. Maybe not if you're talking about really big models. But it's a moderate cost. Okay, so there are so many things you can do to compute this time effectively. The fun part and the real challenge is in getting a good max loss here. So what's the error and how do we choose this this number of exponential terms, this d, right? So that's where approximation theory comes in. So before that, a quick primer so we need to approximate some functions. So how do we go from sequences to functions? We take the generating function of the sequence. So given a sequence C0, C1, C2, we can create a generating function by just multiplying the coefficients by powers of x. So C0 plus C1x plus C2x squared and so on, right? And as an example for this all ones sequence, the generating function it's a geometric series, so we can simplify that as 1 by 1 minus x. This x here is a placeholder symbol. We don't worry about convergence. This is purely, yeah, so just simplify it as we wish without any convergence issues. So we can also go back from this generating function to the coefficients by simply taking a Taylor expansion around 0, right? So it's a lossless representation, so we can go back and forth as we wish. So this has some really nice properties. So when we take this factorization of A as B times C, it turns out that you get the generating function or corresponding generating functions in the same way, right? So the generating function of A, which is 1 by 1 minus x, should be equal to the generating function of B times that of C. Pretty.
So what is the generating function of A?
So that's just, so if you take the first column of a Topliss matrix, and that's a sequence, right? So so we're talking about
A is the top. Okay, so there it's all ones. Yeah.
it's all ones, yeah. So that's how you get this 1 by 1 minus x. And similarly for B and C, we just take the first columns.
But these are finite matrices.
Yeah, so we take them to infinity, yeah. Yeah.
Yeah, and that identity is validated in chain.
Yeah, so I mean, we do all of this with n infinity, but then we can truncate it, right? So all of this holds even for truncated versions of the matrices. So also in our optimal factorization, I said B was equal to C. So the corresponding generating function is 1 by square root of 1 minus x, right? And similarly, if I want to take an inverse, because remember we wanted C inverse Z, that's the noise that we are adding. If we take an inverse, it's like taking a reciprocal of the generating function, right? So it's just square root of 1 minus x. That's the generating function we want to approximate. Okay. So we now got this coefficients as a sum of exponentials where we got a nice recursive form. So what does that look like in generative function world? So a classical result is that if you have so these following three properties are equivalent, right? So if you have a sum of exponential type sequences, that's equivalent to having a generating function which is rational. Right, and the maximum degree of the numerator and denominator is exactly equal to how many terms we have in the exponential. Both are d, right? And both are equivalent to having a linear recurrence of order d. And so all these three properties are equivalent. Where would we have seen such a thing? So the Fibonacci series is probably the most classical linear recurrence. We know the recurrence form, but its generating function is rational of degree 2, and it has a sum of exponential representation in terms of the golden ratio, right? And for those who have more of a signal processing background, very similar things, but with different terminology, right? The generating function is a Z transform. Each of these matrices are filters. And a recursive computation of the output is the same as having a rational Z transform, right? So the ideas are basically all the same, it's just that the language is slightly different. Okay, so the having said all this, the problem we want to do is we started with this square root of 1 minus x function, and we want to approximate it with a rational function because that's what our BLT coefficients gives us, right? So that's the final that's what we are finally after, right? And the key is to connect this approximation quality to our max loss that we actually care about in differential privacy. Okay, so this is the final result. The max loss if our so let's say our Topliss coefficients of C inverse, so that means the first column has a generating function of R. Then the max loss that we get has this correct log n by pi term plus some quantification of the approximation error, right? Which in this case is how close are we to our root 1 minus x optimal generating function, right? And one catch here is that this is in the complex plane. So we want to approximate the square root of 1 minus x on a circle in the complex plane of radius 1 minus 1 by n, right?
Where does the 1 minus 1 by n come?
Very good. So if it's just one, then it doesn't converge because the energy is, so we have to like exponentially decay that, and this decay factor turns out to be like 1 by n. Right? So that's a way of approximating the finite sum, slightly going inside the unit circle. Okay, so leaving aside the fact that we want a complex, an approximation that's valid on the complex plane, in the real.
So then do you really need on the whole circle, or just something like this would be sufficient?
Very good. So here we need it on the circle.
But why? I mean, that will tell you in the whole disk, right? But because anyway, there are no holes inside.
Yeah.
So, but you probably just need a statement of this kind because you're only interested in the real line.
Yeah. So when we tried it out empirically with all possible approximations, the worst approximation was always on the real axis. So I believe at this point that it's the so a real approximation is all we need, but I can't prove it.
No, but the what time? So no. So, in sense, why do you ever even need complex X?
Parseval.
Oh, no, but why? No, so you're going to do some transform. No, so this is the matrix, right? So the coefficients of R are going to give you the matrix.
Yeah. So essentially, it's like in the Fourier domain, right? So we are approximating. So we are integrating over, in the frequency domain.
But where is the frequency?
So if you take this x to be e power j omega, you get a Fourier transform, right?
That is fine, but in your thing, you're just looking at how good the approximation is in the x domain.
Yeah. Okay, so
those x's will always be on 0.
Yeah. Okay, so in a little more detail, what we care about is we want R of x.
Oh, I see. Oh, because you want the coefficients to match up, so you have to Gaussian integral to get the derivative.
Yeah. I mean, it's easier to just do it in the Fourier domain, but it's basically the same thing.
Okay. So that's why you want.
So we want the L2 norm of the row of B and the column of C, and we are computing that in the Fourier domain. Right? So we get a complex integral for that.
So because you have to do the Taylor expansion, is that true? You have to do the Taylor expansion also and compare so you have to compare the coefficients of the Taylor expansion of R and root 1 minus x, root of 1 minus x.
Yeah.
And the way you would do that is to do Cauchy integral for both on this.
Yeah.
And because it's matching up there, you'll be able to bound.
Yeah, that's basically the same thing. Yeah.
I don't see the weird thing, but at least this.
I mean, the idea is the same thing. So if you want to compute the norm of a vector, it's like integrating the Fourier transform. The idea is the same thing. Like the Cauchy integral is just the integral of the Fourier transform. Right? If you
because once you actually start in the integral, because the disk.
Yeah. So it just reduces the Fourier transform. But the idea is the same thing. Okay. So a similar result can be shown for the complex approximation as well. But assuming that's true for now, so essentially this error term that we got is n times exponential of minus root d, right? So this d is the degree, much better than any polynomial approximation we can get. Right, it's exponential, which is fantastic. So it suffices to take this d to be something like log square n to get that extra error term to be additive. Right, so that if we take that as d, that's where we get the result that I displayed in the initial preview slide. Right, so we are getting the best of both worlds. We are getting an additive error with the main leading order term being getting the constant exactly right. And then the extra overhead we are paying per step is polylog. Okay. In practice, we just find these coefficients with automatic differentiation. It's kind of helpful to initialize them with what we get from this rational construction and theory. So there are still some challenges to numerically optimize it, but it works because it's a non-convex problem, right? And the key, as I said, is in the bandit setting, we were looking at polynomial approximations, but now we are looking at rational approximations, which are in general, better. Like Pade approximations, for example, are better than the corresponding Taylor approximations in practice, right?
But that is not like that is still like so this so this one the best rational approximation at mn is still like of the order of
Yeah.
exponential m plus n.
Yeah. So for specific
So it's usually minus d. Where is that?
for special functions, we can do that.
Oh, okay.
Yeah.
For one, okay.
Yeah, I mean there are no poles in that and so on, right? So
Okay. I see. So that is what is.
yeah, that's special here.
Mm.
There are also like other Zolotarev approximations which are known to be like really good at rational approximations.
Okay.
So there are some rational approximations which are special classes which are like really good. But in general, yeah, I mean empirically they're much better though. There are worst case problems where they're no better than Taylor approximations, right? Okay, so empirically, not empirically, it's just a plot of whatever So the square root of 1 minus x is this white line here. This x, 1 minus x is in log scale here. And clearly, like once we start taking polynomial approximations to that, we get really bad approximations, and also the coefficients go all over the place. But on the other hand, if we take these rational approximations, they're much better. Right, so much tighter approximations. Also, these coefficients are not as wide; like they're much closer to the actual coefficients optimal coefficients that we want to run with. Okay, so here's the empirical result. So for the coefficients that we get with 4 buffers optimized to get the best max loss, we find that it's basically indistinguishable empirically from using the optimal coefficients. And as I said, like this, once we get this efficient so in practice, we take this order D to be 4 or something, and that's enough, right? Log n is needed for theory in general. We can show that something that is constant cannot work at all in theory, but in practice, somehow with this empirical optimization, it seems to be okay for the regimes that we care about, right? So this makes it like actually very efficient to run in practice. Okay, so on to the second part. Before that, any questions?
So the rational function that you get for square root or whether that's for square root x, is that something that's easy to describe?
Yeah, we can write down 3 equations to describe it.
Or
Yeah.
So it is done exactly like the definition is exactly what you do for like so you just write down so it's a linear system. It's like as in like you write down you say that I want to match the first so many Taylor.
Oh no. That's what you would do for Pade approximations.
Yeah,
but the construction here is slightly different. Like it's an explicit construction.
Okay.
So you would take like a particular polynomial, and then you would take like say call it p, and then you would do p of square root of x minus p of minus square root of x divided by p of square root of x plus
sequence different from the.
Yeah. It's an explicit construction.
This would be a rational approximation to square root of 1 minus.
To square root of x, but then you can translate it to get square root of 1 minus x. Yeah, translation.
So in this case, you have this 1 by root of 1 minus x. Right? So that the coefficients are some binomial coefficients, right?
Yeah.
It is helpful to look at the function theoretic thing, or you can also look at it from the case binomial coefficients and try to get a rational function there.
Yeah. So I mean they're equivalent, right? So looking at the coefficients directly of the generating function, they're equivalent views. So it turns out those coefficients are not computable directly by any recursion, right? Like you can't compute them in like sublinear time at all, right? So if you want to get like a recursive computation, like you need rational generating functions.
Yeah. But from practical point of view, you could try to play around with those explicit, I don't know, say 2n choose n by something.
Yeah. That's exactly the central. Yeah. Those are the coefficients of C here. Similarly for C inverse, they're also like generalized binomial coefficients. Okay, so I'll be quick in this second part. I'm skipping a lot of details in the second part because we're out of time, but I have backup slides with details if there are questions. So to recollect really quickly, what we are after is this learning problem. I want to minimize the expected loss with data coming from some distribution, and we're in the streaming setting where we only make one pass over the data. So we make a lot of simplifications to get some analytic bounds here. Even with all these simplifications, it was weeks in elliptic integral hell. But some of those are hopefully the simplifying assumptions, right? The first one is asymptotics, right? So we look at what happens in the limit of time tending to infinity. There is so we are looking at the expected suboptimality if we run this algorithm forever, right? And we are going to judge our algorithms based on that. Okay. At a fixed learning rate. So if so we're going to take a fixed learning rate throughout. And it's going to be a function of the coefficients, right? So that's the C prime here. And then the second simplification is to ignore the gradient clipping part. Remember, I mentioned at the start that we have to clip the gradients per example, but that makes it very hard to analytically describe what's happening. It's a non-smooth operation. So we're going to ignore the clipping. That means we don't get any differential privacy guarantees, but we're going to pretend that we scale the noise the way we would for some differential privacy, right? So we're looking purely at the noise dynamics and not at differential privacy guarantees here. Okay, so very simple linear regression problem. Our inputs are zero mean Gaussian with covariance H, full rank. Our linear model is well specified, right? And in this case, what we show is that for independent noise, right? So independent noise corresponds to taking that C matrix to be identity, right? The asymptotic suboptimality of that, it scales with the dimension M of the problem. This rho inverse is some representation of the of how much noise we add for a privacy level, although again, there's no differential privacy here. And as a function of the learning rate, we get just eta, which is the learning rate, right? So if we use a very particular correlated noise, we get an upper bound of an effective dimension. I'll describe in a moment what that effective dimension is. And this eta dependence improves to something like eta square log square 1 over eta times some like smallest eigenvalue of the covariance type of term. And any algorithm for any correlation has to get this effective dimension and has to get eta square. Okay, so that's the lower bound we show. So what is this effective dimension? It's basically the ratio of the trace of that covariance to its largest eigenvalue. And if our covariance is nice and spherical, its effective dimension is high. If it's very close to singular, its effective dimension is low. It's in some sense the measure of how much mass is there, how much signal is there in the problem, right? And it's also closely related to this notion of stable rank, right? So stable rank is the ratio of the squared Frobenius norm of a matrix to its squared largest singular value. And it behaves like the rank, but it varies. It's stable to perturbations in the matrix, right? And it turns out that the effective dimension that we described is equal to the stable rank of the square root matrix. And this stable rank appears everywhere, right? We want numerical algorithms to have that property. It's all over in numerical linear algebra and matrix concentration and so on. So in this case, it's a desirable property, and using correlated noise lets us get that property. So so let's look at this effective dimension versus dimension distinction that we found. And empirically, in simulations that matches almost exactly, right? So this dotted line is what is predicted by theory, and the squares and stars are what we found empirically, right? So the left side plot varies the dimension, the right side plot varies the effective dimension, right? So we see that linear prediction with effective dimension here, with dimension there for independent noise, right? Exactly, almost exactly. And similarly, this learning rate dependence, right? So we said eta square and eta dependence between independent and correlated noise. Things start to break down when we go to very large learning rates. So we know that SGD starts to diverge when you reach 1 over the largest eigenvalue of the Hessian, right? So that's starting to break down here. But with slightly smaller learning rates, that trend is almost, again, exactly found in simulations. There was another algorithm which is a correlated noise algorithm. It's called anti-PGD. It was proposed in a paper that has nothing to do with differential privacy at all. It was proposed as a way of improving generalization in deep learning. And the update basically is a correlated noise algorithm with taking C to be a prefix sum matrix, right? So for C to be the prefix sum matrix, C inverse is this bidiagonal with 1 and -1. And that is exactly what this algorithm is doing, right? It adds some noise and subtracts out all the noise added in just the one previous iteration. So it's a special case of the banded setting that we were looking at earlier. And the sensitivity, because C is equal to A, it's a maximum column norm scales with the number of iterations, right? Because it's all ones, right? So its sensitivity scales, so that column norm is called the sensitivity in differential privacy literature. That scales as n, which means when we are looking at asymptotics here in the so that this doesn't work. Our asymptotic error will be infinity. I shouldn't say not suitable for differential privacy. I should say it's not suitable for our analysis in the asymptotic regime. But even in differential privacy, this cost is too high. Like we wouldn't want to pay that kind of cost. But if we add a small damping factor here in this second term, it turns out that what we get is the geometric mean between what independent noise gets and what the lower bound gets. It's like almost like magically, like yeah, my mind was blown when I saw this. Okay, so in this proof, like because our noise is correlated across time, the usual Markovian or martingale structure, which is leveraged in stochastic gradient proofs, is absent. So again, this analysis is in the Fourier domain. So the results that I showed were for a very particular type of noise correlation, which comes out from the theory, right? It's similar to the optimal Toeplitz matrix, but there is also some exponential decay. I skipped the slide that has the functional form. But it's a new type of correlation which wasn't explored previously in the literature. And although it came out of theory for linear regression, we tried it out on a deep learning problem with language modeling. And we found that it actually works pretty well. We have to tune this one parameter, but modulo that it matches the state-of-the-art approach, in which you find noise correlations directly to optimize the max loss, right, using some semi-definite program. So that's not particularly scalable. Okay, so that brings me to the end. A couple of minutes to just conclude really quickly. We saw that our goal was to find better privacy utility compute trade-offs. In the first part, we looked at the compute aspect without sacrificing the privacy or the utility by using this recursive linear recursions. And in the second part, we looked at learning performance, right, of these correlated noise problems. And yeah, the monograph has a bunch of these details, not of the papers, but more of the foundations. And really quickly, open problems, I was just mentioning this to Piyush a little while earlier. Continuous time limits of this are not known. I think it's very interesting because of this correlated noise structure. Also, on a more practical side, designing adaptive gradient methods to work with correlated noise is challenging because the linearity that we used in designing is no longer there. Right? So one has to be careful about how to design algorithms like Adam in this setting. We have a bunch of other open problems in the monograph. I'm out of time, so I'll just stop here. If there are any interns in this room, please consider applying for MS PhD positions. I was just mentioning earlier that, yeah, I'm looking for MS PhD students. All right, thank you.
So any question for the speaker?
So the binomial thing that Hari was mentioning, so the coefficients you can compute, right?
Yeah.
But you want to compute the evaluations also.
You want to compute the noise with the linear combination of the noise with those
with the coefficient, and
Yeah.
that is
Yes.
what you don't have a recurrence.
Exactly.
So in the deep learning generalization example, you said that you can use Fourier analysis. But when you're optimizing this nonlinear function, doesn't that mess up anything?
So we are so we are taking linear regression, right? Everything's nice and linear. Yeah. Otherwise, it's very hard to get anything analytical.
So any other question from the speaker? If not, so let's take the speaker again.
Thank you, everyone.
We have to stop the Zoom session.
Oh, I just wait the meeting.
Okay, yeah.
I think it should close this.
There's also a session. Yeah.